to point C equals 0. Right? Okay, now translate this equation. You're going to have N1 times this distance, right? Okay, so we can call this distance, give a letter. Let's say L, okay, L here, then L also here. So basically N1 times L, then minus N2 times L equals 0. What does this lead to us? N1 must be equal to N2. Right? So you solve the second equation, N1 equals N2. Now plug into this one. What do you get? So you get N1 equals N2, and it will equal to half P. So the load actually will be equal, evenly distributed there. So we find out the reaction. Now you know N1 equals N2. Okay, now what's next? Now we can go back to what we just said, how to solve it, right? Now we just go moving. What's next you can find? You can find the stress.
So we're going to do that just over sigma 2, since that would be our weak point?
Okay, so you do over just 1, or you should do it 2?
2.
Because you want structure safe. Now your structure including 2 bars. So you want to make sure this bar is safe as well. So you need to check twice. Check this one and this one. Okay, so we do that. So you calculate sigma 1 equals to N1 over A1. And then sigma 2 equals N2 over A2. Right? Okay, so let's do this one first. Okay, what's A1? N1 half P. What's the value?
5,000.
Will be 5K, right? Okay, so 5K here over, what's A1? 20 millimeter squared, right? Okay, what's A2? 10, right?
I've got 250.
See here, A is giving 10 millimeter squared. Okay, so you can calculate the value. Anyone?
I've got 250 megapascals, which is
250 megapascal here, right?
Way past 50.
Okay, what's here? This will be.
I'm sorry, yeah. So that would be.
See, 5 divided 2.
Would be 500.
That's 250. So this will be 500 megapascal. Okay. What's the conclusion?
That it's too much force. Or
it's already too much, because here you see this allowable will be only 50, right? Now what you can do?
Decrease the force or increase the
Decrease the force, right? How can we adjust the load, make it safe?
Go with 2 kilonewtons.
What if we divide by 10? Divide load by 10.
Yeah, that'd be fine.
So you change the P to 1 kilonewton. Then your sigma 1 will be, actually I'm jumping too fast. Maybe I'll just say, if change P to 1, then what's N1? Equals N2.
I can't see what you're doing, doctor.
Right? Okay, now then sigma 1, sigma 2. What's the sigma 1?
You cannot see what you're writing.
Oh, sorry. Okay, so here. So sigma 1 will be equals to 25 megapascal. And sigma 2 will equal to 50 megapascal. Right? Because I shrink everything 10 times. Right? Okay, is this safe enough?
Yes. It's pushing it. It's there.
Is this safe enough? No. Because the bar sigma 1 is fine. Right? It's right there. Because this one we say is equals 50. That's allowable stress. That's the limit you can go. Okay, so this one is fine. But this one, it's right there. Right? So you may want to reduce a little bit. It's right at the limit. Right?
So technically, I would say that's a no-go.
Technically, if I'm really build this structure, I won't go this way because it's right at the limit. You want to reduce it to maybe 49 or something, right? You want to change it a little bit, make sure it's the same. Right? So basically, that's you judge it here. Okay, yes?
When we're counting stress, you're dividing 5,000 by 20 millimeters squared. You need to convert the millimeters squared to meters squared.
Counting which one?
On the, I guess, sigma 1 and sigma 2, you're dividing 5,000 kilonewtons by
There are
20
5,000. I don't see a 5,000 there.
5K.
Half your P.
Meter squared instead of millimeter squared.
Half the P, so P is 1, right? So half the P basically is N1, N2, that's 0.5.
But so when we divided it, you need to change the millimeter squared to meter squared?
Yes, that's why you have this megapascal here.
Oh.
So you already convert the units. So this is millimeter square, right? Millimeter square, that's 10 minus 6 meter square. That's where this M come from.
Okay.
Right. So you need to do the unit conversion, yes. Right. I kind of jumped there. All right. Okay, so here is an example. I basically use equation of equilibrium, find the local force, calculate the local stress, compare to your allowable stress, then see if it's safe or not. Right. So you say again, you need the equation of equilibrium. Right. Okay, that's one point. Second point is, if you have multiple parts in a structure, you need to check multiple ones. So you need to check sigma 1, check sigma 2. So check piece 1, piece 2. They both safe, and then you're okay. Change the screen to different screens. It's on. Maybe I'll talk to you after the class. Yeah, I'll come to you after. All right, sorry. Okay, so any question about this example here? Yeah. It's a 5. Which one? You talk about force or you talk about stress? The force here is 5 kilonewton. First unit is Newton. So stress is a Pascal.
She's forgetting to square her millimeters. That's probably what's
the millimeter is millimeter square.
It's
Because I give you area.
It's 1,000 squared, not 1,000.
Okay, yeah, 1 meter is 1,000 millimeter, but 1 meter square is a 10�6, right? Millimeter square. I'm not giving you the diameter. I'm giving you here the area already, so you don't need to calculate the area. Oftentimes, the homework problem either give you a diameter or give you the side, how wide they are, right? Then you need to calculate the area. But anyway, here I'm just making it easier, simple calculation. So I just directly I give you the area. All right. Okay. Any other questions? Okay, if not, let's move on. We need to talk about, so this one, I have this slide here, kind of summarize what we cover in chapter 1. And I believe this one already online, so you can actually print it out if you want. So this kind of summarize pretty much everything we cover in all the concept in chapter 1. All right? Okay, so now we need to move on to chapter 2. Okay, so basically, chapter 1 gives us the basic concept about stress, strain, safety factor. Okay, from chapter 2 on, we're going to look at the parts of a structure. So for a complicated structure, we're going to break it down into pieces. Look at each piece, what kind of load is under and what kind of stress is there, how you make it safe, what's the high stress, how the stress is distributed, all this kind of question, right? So basically, we divide the parts we see in common engineering structure into several models. One we call a bar. Okay. So basically, technically called axially load member. So basically, you apply an axial load, and that's how it deforms. That's one. Then we're going to talk about the shaft, a model shaft. That's basically a bar. You apply a torque at the end, twist, how it twists, or torsion. That's the chapter 3. Then we're going to talk about a bar that under lateral load. As a beam, we call beam model, how it's going to bend, how to deform, the stress and deformation. And then we talk about a column. So if you have something here, right, you apply load from the top, and that can actually sometimes have stability issue. We talk about stability, that's chapter 11, we talk about that. Okay, so we're going to go over different models, looking at how it deforms, how this thing. So we're going to repeat it again and again, all right? But the first one we're going to look at is just a actually loaded member. You have a long bar, a cylinder bar, and you applying a load there, compression or tension, and see how it deform. What's the stress going to generate in this bar? All right. So is this really here? You have you draw a bar. Now in this chapter we call it a bar, right? Or some you want to say, oh, it's a cable. That's also is a bar, right? Or a wire can also be a bar, right? Or a stick or a beam. If I load axially, I don't call it a beam. I call it a bar. Right? So the character is you have very long dimension L is bigger than your cross section. So a long one, right? So you can treat it as a uniform one. The reason it's longer. Okay, then you apply load P here. Right? So the basic question is when you have a structure like this, what's the stress in this bar? And what's the strain in this bar? And what's the elongation, deformation of this bar, right? That's going to move here. That's the three basic questions we want to know. All right? Actually, in chapter 1, when we define stress, we already kind of gave the answer to this question. Right? Anyone recall what's the stress if you apply load P here?
P over A.
P over A, yes. So it will be P over A. So we already know about it. Is this large enough? You can see?
Yes.
Okay. All right. So we already know about it. Now, how you calculate the strain? It's the elongation over the length. Right? Okay, now, how you calculate the total elongation?
Delta L.
We actually talk about that. All right? Because here, this two equation, here is the delta. If I know strain, I can determine the delta. Right? Now, if I know the load, how can I find out the strain? What's the relation between stress and strain?
Hooke's law.
Hooke's law, right? So the linear relation. So between this one, we have a bridge. That's called Hooke's law. Stress and strain, they're linked this way. Okay, now can we combine all these three equations together and find what is the elongation? Actually, we did that practice once earlier, right? Okay, so let's combine. We need to find out delta. So I just write everything together here. Delta equals what? According to this equation, delta equals to, actually not over, it's actually, let me put it this way.
Yeah.
Delta equals L times
Strain.
strain. Okay, what's the strain? Strain is stress over modulus, according to this equation. Now, what's the stress? So it's L over E, and then stress is P over A. Right? Okay, combine all together. I have this equation. It will be P L over E A. That's the equation. So this is called elongation equation. Right? Well, of course, elongation can be a shrinkage. Right? When you have a shrinkage, it's a positive, it's a negative elongation. So the basic deformation will be you stretch it longer or you compress it shorter. Right? Yeah.
So we're getting our elastic modulus from a table, or is it given?
Depend. Okay. So this is just the basic relation, right? This is model equation. This is the basic equation. Give you a relation between all these variables. Right? Depend on the situation. Okay. Let's say I know the material. You can find the modulus from another test or from a manual, and then you can use this to calculate this strain. I mean the elongation. Okay. In another situation, I have some material here. I present to you. Can you find out the Young's modulus for me? You can use this one, design experiment. You do a test, you stretch, you know the load, you measure the elongation. Then you can use this equation, basically figure out what's the modulus. Right? So basically that's all different type of questions I can actually ask you. Right? This one just say it's a relation between all these 5 variables. I can give you all 4 and ask you for another one that you don't know. Right? Okay. All right, so the equation is really simple. You just use this one to calculate. But here are a few things, actually, based on this equation, I want to explain a little bit what actually there. Okay, so this equation calculates the elongation. Right? So elongation of this segment that under load P, and the cross-section area is A, length is L, and the material modulus is actually E, right? That's the relation for heat. Now, if you go back to what we just did, this example. Okay. Now, if you try to calculate the elongation, now here you're going to have two elongations, right? Those two bars, their axial and the axial force, and they're going to elongate. Now they're going to have two different elongations. Is that correct?
Looks like it.
So when you calculate the elongation of this one, okay, that's the key. You have to use the length of this one, modulus of this one, force in this one, and the area of this one. So every parameter needs to come from this one. Then you determine the elongation of this one, right? And then for this one, it's the same. You use its own, basically its own dimensions to calculate its own deformation, all right? So this is easy to say, but oftentimes we make a mistake. For example, when you calculate the stress in sigma 1, okay, people sometimes just use N2 to calculate. All right? In this problem, seems a little bit weird. Later on, you're going to see there are cases we often confuse what stress to use there to calculate. All right? Okay, that's the first point. All right. Second one, I want to do a little bit twist of your mind, say your judgment, give your feeling how this relation links things together. All right? Okay, so here's my quiz questions. All right? So if I have this bar, right now you have a load P applying to this A, E, L, you all know, right? So you get this elongation will be delta, right? Now, what if I have the same bar? Okay, somehow I double the load, so I have 2P, the same bar, A, E, L, the same. Okay, how much elongation are you going to get?
Double.
Double it, right? You put this equation, you'll find it will double. So basically, you're going to get twice the elongation, right? Okay, now, what about the stress in this bar, right? Previously, you get stress, it's sigma. Strain is epsilon, right? Because all this equation we already have. Now, in this new situation, you have twice the load. Now, how does the stress change?
It's twice.
Twice, right? Because the reason is here. So let me put the equation here. Sigma equals P over A. And then sigma equals E over times epsilon. And then epsilon is delta over L. That's all the equations we have. Right? This one is coming from this 3. Okay, now this will be twice the stress. Now what about strain?
Half.
I heard a different one.
It
Half,
is twice.
double, or same?
It's twice.
It's double. Okay, why? Because when you have twice the load, stress double, right? Same material, stress double, E, epsilon mass double. So basically, you're going to have twice the epsilon. Okay, that's an easy one. Now, let's say I apply just one load here. I don't change the load. Okay. Now, I double the area. I have the same E and same L.
Everything's half.
Everything's half. So first, stress will be half, right? Okay. Strain, accordingly, will be half. Now, elongation will be half, right? Okay. Now, what if I apply this load, same area, same length, but I double the modulus? I'm using a different material, a stronger, stiffer material.
Twice.
Okay, how does the stress change?
Twice.
Half.
Say double.
Now, say it.
No, half.
How you determine the stress? Load over area. Did the load change? Did the area change? Then when you say stress change,
I'm looking at your modulus.
you look at the wrong equation.
Yeah,
right?
I see.
So basically, you need to get familiar with all the 3 equations to feel how things are changing there. I think that's kind of feeling, engineering feeling. Okay, that feeling will help you actually make a lot of judgment, kind of intuition, to judge there's something wrong in your design or problem there. For example, I want a stronger material, right? Somehow, the load can be higher, so I can carry more load. Now, if I increase the load, you don't select a weaker material. That's the common sense. That's the intuition. That's what I'm trying to help deal with. Okay, so what's the stress?
It's going to be the same.
Will be the same. Okay, so it's the same. Now, stress is the same. Okay, what about strain?
Twice.
Which equation you use? Look at this one. Stress is the same.
That's right, if it doesn't change.
E double. What's the strain?
It's to half.
Half. Right, so this will be half. Okay, now what about elongation?
E, it's going to half.
Everything else the same, except E is double. So delta will be half. Right? Okay, you can do keep this all the time, right? Let's do another one. Same load, A, same, twice the length, same material.
Sigma stays the same.
Okay, sigma stays the same.
Your elongation will half.
What about strain?
Your strain halves.
Okay, or which one easier? You can judge what's the elongation. Look at this equation. What's the elongation? See, this will be double. Same, double. So delta will be double. Right? Now what about strain? Half? How do you determine strain? Now, see here, strain is calculated by elongation versus length.
Oh, it stays the same.
You double the length, you double the elongation. So strain is
Pay attention.
the same. Alright? So this will be the same. Okay. Okay, when you go home, play with this game. Alright? Change it, go up or go down. Get a feeling how things are changing. Just set up a feeling, kind of give you a feeling. Later on, you can judge whether your solution will be correct or wrong there. Give you some common engineering things. Alright?
Because your elongation also doubles, so they cancel.
Okay, any questions here? This is a fun practice, right? If I give you a quiz, something related to this, can you do it? No? Okay, then I need to give you a quiz. Because you cannot do it. If you all can do it, then I don't have to give you another one. Right? Okay, any questions here?
So it's basically an order of operations that you need to pay attention
Yeah,
to.
so basically, the three equations there. You see which one is changed, which one doesn't. You put it into the equation, then you make a judgment. All right? Either use the three separate equations or use a combined equation. Basically, you have like a 4 you can directly use. Right? Although they are not independent, but they help you judge how things are going, changing. All right?
So would you recommend we start with the elongation formula?
Actually, yes. My recommendation, if you want to judge the elongation, you start with this one. And then you say which one is changing. Right? There are possibilities. For example, I can give you combinations. I increase the load twice, but I change the length, double the length, or reduce the length, then what's changing there? So I can give you all this combination of changes. And you need to be able to judge how things are changing. All right? Okay. Any questions so far? Okay, here's another example. All right, say I have a bar. I know all the dimension, AEL, all known.
Is that 10 or 0? What is that second
Oh, sorry, it's 10, meaning 10. All right. Okay, so I have this bar here. At the end, I apply 2 load P here, and they're to an angle. All right. So let's say I know the angle. Make it either. Let's say this is a 45 degree or 30 degree. Look like 30, right? So let's say 30 degree and 30 degree here. All right. Now, my question will be, if I have this bar here, I apply this 2 load. This happens, right? In real life, someone pulling a bar, right? So if I apply this 2% applying equally 10 Newton here, right? So what's the stress in this bar? What's the elongation of this bar? So the question will be, what's the stress in this bar? What's the elongation in this bar?
I'd say stress is going to be 2 times P times the sine of 30 degrees.
So here is my quick solution. Sigma equals P over A, right? So therefore I have 10 over A. Because you say equations say P over A. I'm using P over A. Is this correct?
No.
What's wrong? Okay. You're not understand what's the equation mean, right? This equation means the load in this part of the bar. And that P given here is not the load in the bar. That's why we emphasize on internal load or internal force. Right? Actually, that's the term we use very common. Internal force. So you have to find out in this bar what's the force. Then you put it into this equation to calculate. Right? So the load P here given is not the load in this bar. Therefore, you cannot use it. Right? And for this reason, actually, oftentimes I change this equation to call this N over A. Means N is the internal force. You use the internal force. Right? And in the other equation, I use actually NL over EA. Okay. Sounds like just a small play of letters. You change that. But basically, I'm trying to remind you, you need the local internal force to put in the equation. All right. Okay, once you realize this, now next step is find out the internal force. Okay, so how can we find the internal force for this problem?
You're going to have to do a cosine.
To do a cut, right? Free body diagram. Okay, I need to find out the internal force in this bar, right? So I make a cut here. Okay, once I make a cut, then I can draw the free body diagram. Right? So you have a 30, P equals 10 here, and then you have a P equals 10 here. Now what's here?
N.
That's the reaction N you're looking for. Right? So this is a completely free body diagram. I cut this part as free body, and then I draw all the load reaction. That's a complete free body diagram. Right? Okay, with this one, now I can write equation of equilibrium. So what's the equation of equilibrium?
0.
I just need 1 actually. Sigma Fx equals 0. And that gives me negative N plus
Equals
P, this one, project to the x direction. Cosine 30 degree. Right? And then you have another one.
times 2.
So this 2 equals, so twice and equals 0. And from here you can find out the N. Once you find out N, next you calculate stress.
So that's 10.
So I want to emphasize the stress you put in this equation. They are the local internal force. Right? Okay, remember you need the local stress to calculate the local information, local dimensions, local force to calculate the local stress. Right? It's like you calculate, right, how much money you can spend. You can only calculate your salary. You cannot count somebody else's salary. Right? If this room we get lots of money, but not necessarily mean you have a lot of money. So you have to count your locally. Your monthly salary, you cannot count everybody else's income. Right? Sounds very easy, simple, but oftentimes we do make a mistake. All right. So last, let me end with this question. Okay, what if I have a bar? All right. Now, I make a hole here.
Oh, what? A hole?
A hole, empty, hole inside. Okay, a hollow bar, right? So when I apply load P here, right? I know all the dimensions. I know the material. So I know this one is L. Let's call it L1. So this part is also L1. This part is L2, right? And I know all the A's. So this part will be A2, and the other part without the hole is A1. And the material, I know the modulus is all the same. Okay. Now, for this bar, if I apply a load P, I know the value. Let's say 10 Newton. Right. Now, how can you determine the stress in this bar, whether it's safe or not, right? We need to find out stress. And then how do you determine this bar, how much you're going to elongate?
So you're looking at a sigma max is what you're asking for here?
Okay, I need to find out the stress in this bar. Make sure it's safe, right? So what I need to find out? Need to find out the maximum stress. As long as the maximum stress is safe, then everywhere else is smaller, it will be safe.
So I do the stress at A2.
Okay, so how can you find the stress in this bar?
P over A2.
Okay, so I have, let me write on a new piece of paper. More space. All right, so I'll write down on here. Okay. So I need the stress, right? So I calculate stress will equal to P over A. That's the equation says. Right? So I put it here, say 10 Newton over A. What's A?
Two different ones.
There are two A's. Then what should I do? Okay, your common sense. Okay, what happens if you have a bar that has A1 and A2?
It will fail at A2.
Are they, this A1 part, A1, A2 part, are they be the same?
No.
No.
The stress, will the stress be equal in this
No.
two portions?
Different.
It will be different. Okay, once you realize that key concept, now what do you need to do?
Find the weak.
You find out, now this will change to, you need to find out sigma 1 and sigma 2. Then find out the maximum. Right? So basically, we need to divide it up. Right? Divide the segment. Okay, so what we have is what we call a non-uniform. Okay, non-uniform bars. That's the concept. So you have a bar that's not uniform. All right? Therefore, you cannot directly use this one equation to give you the value, determine the elongation or calculate stress. You have to divide up, calculate each segment locally. All right? So that's the concept, non-uniform bar. We're going to continue to cover. But here, just quickly, let's see how you get the stress sigma 1. You find out what's the stress in this segment, right? What's the force in this segment? Can we find the force here?
Well, the force is already there. It's uniform, yes?
It's a uniform, right? Why is it uniform? Because I can draw a free body diagram. Let's say I make a cut here. So I draw it here, right? This is a free body diagram. So you have P here. And then this will be local N1. Now what if I cut here?
Same.
I cut here, right? So I have this bar showing here. This is a free body. Okay. Now this is the P. So this will be N2. Now is N1 equals N2 in this case?
Yes.
Yes, they have to. Otherwise, one of this is not in equilibrium. Because this one in equilibrium, N1 equals P. This one in equilibrium, N2 equals P. They both equal to P. So therefore, the force in this bar here is the same everywhere. Okay, but the area is not. So you have to calculate. This will be N1 over A1. This has to be N2 over A2. Right? So you calculate local stress using local force. You calculate this local stress using this local force. That's basically the concept. Okay, last question. Now how you calculate the elongation? Can you use this equation and say, okay, the P times L over EA?
Could you sum your lengths and